Well, in this video, we're going to do an example of Euler's method based on a differential equation that we actually know the solution of. So we'll be able to compare the approximation or the estimate we get using Euler's method to the true value. Okay, Euler's method to estimate y of 3. And y is a function of x over here, but I'm probably going to refer to it as time, so I may be thinking of x as being the time axis. So y at time 3, given this differential equation, which we've already solved in an earlier video, but this is our function of x and y, and we're given that at time 0, y is equal to 5. At time 0, and now we're trying to estimate out to time 3. So initially, I wrote the formula for Euler's method right here. We'll know this, we'll know everything on the right, and then this will be our estimate of y of I plus 1. So we start off at I equals 0. Because we know x naught is 0, y naught is 5, that's what we're given. And then h, our step size, has to be 3 because we're going to go from 0 to 3 in one single step. One step means h is equal to 3. Okay, so I0 would give us the formula y1 equals y0 plus f of x0 y0 h. So let's just plug it in and see what we get. y1 is equal to y0 is 5 plus f of 0, 5. Okay, there's f of xy, or I wrote it as yx. X is a 0, so we get 3e to the negative 0 minus 0.4 times y is 5. Times h, which is the step size, which is 3. So that gives us 5 plus 3e to the 0 is 3. 3 times 1. 0.4 times 5 is 2. So we've got 3 minus 2, which is just 1 times 3. So we get 8. That's our approximation. Our approximation of this function y at time 3 is 8, and that's a poor estimate because the true value is y1 is equal to 2.763. That's the true value. So we could compute our error. Our true error is 2.763 minus 8 in absolute values. So this is our true absolute error. And that's equal to 5.273. And if we wanted to get our, I usually use this epsilon for a relative error. And that would simply be this divided by 2.73. We'll go ahead and write it like 2.763 minus 8, which we know is 5.273, over the truth. And that would give us a 1.9, which is 190% relative error. That's a terrible estimate. But the reason is we only used one step, and it's a huge step size from 0 to 3. And we used a straight line to get our estimate of y1. Okay, so now let's go to doing it one more time, and we'll get a little better answer. This time we're going to do 2 steps, which means if there are 2 steps going from 0 to 3, each one of them is going to be 1.5, 1.5. So we're going to go basically from 0 to 1.5 and then to 3. So it takes 2 steps. For I equals 0, we get, well, this same formula. I won't write it again. But we would get y1 is equal to 5 plus f of 0, 5 times h, which is 1.5. So I'm taking an additional step here. I just wrote f of 0, 5. Now I need to plug that in. And that's going to be exactly the same as last time. This number right here, I'll go ahead and write it again. 3e to the negative 0 minus 0.4 times 5. That whole thing in parentheses is just 1, but this time it's times 1.5. And we get 5 plus 1.5, which is 6.5. And to save a little bit of room, I'm just going to put 6.5. So that's not our estimate at time of 3. That's halfway there. That's our estimate at the time of 1.5. Okay, so now we have one more step to do. We're going to go I equals 1, which, since I haven't written that one out, I'll write it out. y2, I is equal to 1. So y2 is equal to y1 plus f of x1, y1 times h. That's the formula we'll use for the second step. And we've got x1 equaling 1.5, we know that. y1, we have what we computed, 6.5. I'm going to put a star by it because that's not the truth, that's just our estimate. And then h equals 1.5. So, y of 2 is equal to 6.5 plus f of 1.5 comma 6.5 times 1.5, that's h. And that gives us 6.5 plus 3e to the negative 1.5 minus 0.4 times 6.5 times 1.5. And if you work that out, you get 3.604. So that's our approximation of y at the time x2. x0 being 0, x1 being 1.5, x2 being at 3. So y2. So we get the true error at 2.763 minus 3.604. Our true error is negative 0.0841. I'll take the negative sign off because we made it an absolute error. And then the relative absolute error would be this number, 0.0841 over 2.763, which gives us about 30.44%. So we're still at a poor estimate. But a step size of 1.5 is very large. So just as a final note, decrease step size. If you just decrease it, that implies better estimate.